Welcome to the deep dive. This is where we take the stack of sources you, the learner, give us sometimes a really eclectic mix like today, and we synthesize it all down into something memorable, something useful.
And today's stack is definitely, well, eclectic is the word. It's got this moody, almost atmospheric feel starting out. We're going from the aesthetics of dark flowers, like really dark flowers.
The black ones.
Yeah, the so-called black ones, and then diving deep into the genetics behind that color. Then we swing over to human stress, performance psychology, and even touch on engineered health through biotech.
And just when you think we can't possibly connect more dots, we end up in deep space looking at analytical science and the hunt for exoplanets. It's quite a journey.
It really is. But our mission, as always, is to find the connections, to weave these threads together for you. So the starting point, this initial theme, is the allure of black in nature, particularly in the garden.
Okay, let's unpack that. The dark side of the garden.
Right. So the first thing all the sources seem to agree on is that, botanically speaking, true black flowers are, well, mostly a myth. They're extremely rare, maybe even non-existent, depending on how strict your definition is.
So when we talk about black flowers, what are we really seeing?
We're seeing incredibly high saturation. Think deep, deep eggplant purple, or a really dark maroon, sometimes a dark chocolatey brown, or a super concentrated crimson. They look black because they absorb so much light.
And that's what gives them that drama in the garden, right? That visual weight.
Exactly. They create contrast, depth.
Oh.
One source even called them a visual rest stop for the eye amidst brighter colors. It makes you pause.
So for you listening, if you're thinking about using these in your own garden, the sources highlighted some really standout examples.
Definitely. Starting in late spring, you've got the classic Queen of the Night tulip. It's almost iconic for that near black look.
It's more of a deep, deep purple, though, isn't it? Especially in full sun.
It is, yeah. A very sleek, dark plum purple. But in shade or twilight, it reads as black. It's pretty hardy, zones 3 to 7. Needs that full sun and good drainage. Looks amazing against its own bright green leaves.
Okay, but what if you have shade? That's always my problem, Eric.
Then you look towards the hellebores. Specifically, the sources mention hellebore midnight ruffles. Hellebores are fantastic anyway because they bloom so early, sometimes when there's still snow.
Seriously tough plants.
Absolutely. And midnight ruffles has this incredible, rich, velvety texture and that deep, near black color. And loves shade, prefers those damp, cooler spots, good for zones 3 through 9.
Now, there was one that sounded less like a garden plant and more like something from a sci-fi movie. The bat flower.
Oh yeah, the bat flower, Paca chantrieri. It's definitely theatrical. The descriptions use words like otherworldly, eerie. It has these large, dark, sort of wing-like bracts.
Like bat wings, hence the name.
Exactly. And then these long, thread-like filaments hanging down. It really does look like a bat in flight. Blooms around October, November, which adds to the spooky vibe.
But tricky to grow for most people. Needs tropical conditions.
Very much so. Zones 9B to 11 needs low light, high humidity. Probably more of a greenhouse or conservatory plant, unless you're in a very specific climate.
Okay, and before we get to the star of the dark flower show, we have to address the elephant in the room. The black rose. Does it exist?
Simple answer, no. Not a truly black one anyway. The sources are clear on this. After centuries of trying, the darkest roses breeders have managed are extremely deep reds or burgundies, like black picara.
So if you see a perfectly black rose...
It's almost certainly dyed. Florists might spray them or use dye uptake through the stem, but it's not natural pigment.
Which makes the achievement of the black velvet petunia even more remarkable then. Petunia ex hybrida. The sources called it the holy grail for breeders.
They did, because it got closer to a true, deep, non-reflective black than pretty much anything else out there at the time. A really velvety, light-absorbing texture on the petals.
And the key thing here, which you mentioned earlier, is how they made it.
Right, this wasn't genetic modification. It was 4 years of painstaking traditional breeding by Jian Pingren. Cross-pollinating, selecting, cross-pollinating again, thousands and thousands of times.
Just trying to concentrate those dark pigments through selective breeding.
Exactly. Old school plant breeding, just pushed to the absolute limit to maximize that color density.
Okay, so you've got this incredibly dark flower. How do you actually use it effectively in a garden design? The sources had tips on this, right? Because dark colors can just disappear if you're not careful.
You absolutely can't. You put a black flower against dark soil or deep shade, and poof, it's gone. So the strategy is all about contrast.
Make it pop.
Precisely. Pair the black velvet petunia, which is usually grown as an annual, zone 710, loves full sun. Pair it with something bright, Silvery foliage like Dusky Miller's classic. Or stark white lilies, vibrant yellows, electric blues. Something that makes the black stand out.
And layering, too, I think,
Yeah.
using different heights.
Yes, essential for depth. You could use the low-growing petunias at the front of a border, and then behind them, something tall and dark, like the black hollyhock nigra, that can get 6, even 8 feet tall.
Wow, that would be dramatic. A real Gothic look.
Totally. Or you could create specific themes, like a moonlight garden using whites, silvers, and these deep blacks that gain mystery after dusk.
It's fascinating how much thought goes into using darkness aesthetically, but it really forces the next question. How does the plant actually make that much pigment? What's happening at the molecular level?
Exactly. And that pulls us out of the garden bed and straight into the world of genetics.
Okay, so we established the black velvet petunia isn't truly black, it's just packed, absolutely stuffed with dark pigments. And those pigments are anthocyanins.
That's right. Anthocyanins are a class of flavonoid compounds. They're water-soluble pigments, and they're responsible for almost all the reds, purples, and blues you see in flowers, fruits, even some leaves in autumn.
So how does a plant actually build these molecules? Is it like an assembly line?
That's a perfect analogy. It is like an assembly line known as the flavonoid pathway. And like any factory line, you got two main groups of components.
Yeah.
The workers actually doing the assembly, and the managers telling them what to do.
Okay, let's start with the workers. The sources called these the structural genes, right? The enzymes.
Exactly. These genes code for the enzymes that perform the chemical reactions, step by step, turning simple precursor molecules into complex anthocyanins. The sources mentioned a few key ones in petunias: CHS, DFR, ANS, UFGT.
Can we quickly break those down? What do they actually do?
Sure, think of CHS, chalcone synthase, as the very first worker on the line. It takes the basic starting materials and performs the first key step, creating the core flavonoid structure. It's fundamental.
Got it. Entry point.
Then further down, you have enzymes like DFR, dihydroflavanol 4 reductase, and ANS, anthocyanin synthase. They modify that core structure, getting it closer to the final colored form.
Yeah.
ANS is actually the step that creates the colored molecule from a colorless precursor.
Ah, so ANS flips the color switch.
In a way, yes. And then UFGT, UDP glucose, flavonoid 3O glucosyltransferase, comes in at the end to add a sugar molecule. This stabilizes the pigment, makes it soluble, and can also slightly modify the final hue. So these are your essential hands-on workers.
Okay, workers covered. Now the management team. The regulatory genes.
Right. These are the transcription factors, TFs. You might see families mentioned like MYB, BHLH, WD40. These proteins don't actually touch the pigment molecules themselves. Instead, they bind to the DNA near the structural genes.
And control whether those structural genes are turned on or off.
Exactly. They control if, when, where, and crucially, how much those structural genes are expressed. So the incredible darkness of the black velvet petunia isn't because it has better structural genes. It's because its regulatory genes are telling the workers to go into overdrive, to produce massive amounts of anthocyanins.
It's about turning the production dial up to 11.
Precisely. And this is where the research on the whole Petunia group of plants gets really, really interesting. Scientists looked at the rate at which these different genes evolve across related species. They measured something called omega.
Omega, that's a measure of evolutionary speed or selective pressure.
Basically, yes. A low omega, close to 0, means the gene is under strong, purifying selection. Any changes are harmful, so evolution weeds them out very quickly. The gene changes very slowly over time. It's highly conserved.
Like a vital piece of machinery you don't mess with.
Exactly. A high omega, closer to 1 or even above 1, suggests selection is relaxed, or maybe even positive selection is driving rapid changes. The gene is evolving quickly.
And the study found huge differences in omega across these flower color genes, like 7-fold differences.
Massive differences, and the pattern was incredibly clear. The structural genes, the workers like CHS, DFR, ANS, they are evolving very, very slowly. Well, CHS, that first gene in the pathway, had the lowest omega value observed in the whole study, just 0.09. That puts it in the same category as fundamental housekeeping genes essential for basic cell survival, like actin.
Wow. So the core machinery for making color has been basically locked down by evolution for millions of years. It works. Don't change it.
Seems like it. But then you look at the regulatory genes, the transcription factors, and they are evolving, on average, 1.8 times faster than the structural genes they control.
Wait, faster? How does that make sense? Wouldn't changing the managers more often lead to chaos on the assembly line?
That's the fascinating puzzle. The sources point to a couple of interconnected ideas. First, specialization. A lot of these TFs, especially the MYB types, are only involved in making flower color.
Okay.
So if a plant lineage switches pollinators, maybe it evolves white flowers to attract moths instead of bees, it doesn't need those specific color-producing TFs anymore. Selection pressure on them relaxes. Mutations can accumulate faster, driving up that omega value.
Ah, so if you stop needing the tool, you stop caring so much if it gets a bit rusty or bent, the evolutionary quality control slacks off.
That's a good way to put it. The second reason, and this is maybe even more profound, relates to how much these genes are used. There's a strong inverse correlation found between the evolutionary rate, omega, and the gene's expression level.
Meaning genes that aren't used very much evolve faster.
Exactly. The structural genes, the workers, they're often expressed at relatively high levels, churning out enzymes constantly. But the transcription factors, especially those fast-evolving MYB regulators, are typically expressed at much, much lower levels, like 15 times lower on average.
Okay, why would low expression lead to faster evolution?
Think about the consequences of a mistake. If a gene is highly expressed, a mutation leading to a misfolded, non-functional, or even toxic protein product could be really damaging because there's so much of that bad protein around. So evolution strongly selects against any changes.
High stakes for high expression genes.
Right. But if a gene is only expressed at tiny levels, maybe only in specific cells or at specific times, the potential damage from a mutation is much lower. The cell can kind of tolerate more sloppiness in the genetic code for these low-expression genes. Purifying selection is weaker.
So lower expression means lower risk, which allows for faster accumulation of mutations and thus faster evolution.
That's the leading hypothesis. And the big implication is that these fast-evolving, low-expression regulators are the primary drivers of major color shifts between species. When you see whole lineages lose color, like the white-flowered Bernfelsia or Nirenbergia relatives of Petunia, it almost always correlates with mutations or deletions in these key regulatory MYB genes, not the structural ones.
The managers quit or change the instructions, not the workers refusing to work.
Generally, yes, though the research also added a nuance. Changing the intensity of color, like making a purple petunia into the super dark black velvet, might not always involve big changes in the omega rates themselves. It's more about fine-tuning the level of regulatory activity, tweaking that production dial.
It's incredible how understanding these genetic control switches, discovered by studying flower color, has opened doors in completely different fields, like human health, right?
Absolutely. The knowledge of how to precisely control anthocyanin production is now being used in very sophisticated ways in biotechnology.
Okay, so let's take those anthocyanins, the pigments making flowers dark, and shift focus. They're not just about looks. The sources highlight major health benefits. Powerful antioxidants.
Yes, very potent. There's significant evidence linking anthocyanin consumption to reduced risk of cardiovascular disease, certain cancers, and general anti-inflammatory effects. They mop up harmful free radicals in the body.
Which led directly to the Purple Tomato Project. This sounds fascinating, taking a regular food and turning it into a superfood.
That was exactly the goal, led by Professor Kathy Martin's group. Tomatoes naturally have the genes for the anthocyanin pathway, but they're mostly switched off in the fruit. They wanted to turn them back on, specifically in the part we eat.
And they used what they learned from flowers, applying that knowledge of regulatory genes.
Precisely. They used genetic modification, GM, to introduce two key regulatory genes transcription factors borrowed from the snapdragon flower, Antirrhinamagus, which is known for intense flower colors.
But they didn't want purple leaves and stems, just purple fruit. How did they target it?
This was the clever part. They linked those snapdragon regulatory genes to a fruit-specific promoter sequence taken from the tomato's own DNA. A promoter is like an on switch for a gene, and this specific one only gets flipped in developing fruit tissue.
So the instructions to make purple pigment only get read inside the tomato itself. Elegant control.
Very elegant. And the results were striking. They fed these high anthocyanin purple tomatoes to a strain of mice genetically prone to cancer. They lack the p53 gene.
The results.
Mice on a standard diet lived about 142 days on average. But mice whose diet included 10% purple tomato powder lived significantly longer, an average of 182 days.
Wow, a 40-day extension. That's nearly a 30% increase in lifespan in that model. And regular tomatoes didn't have that effect.
No, the study confirmed the benefit was linked to the high anthocyanin levels, not just eating tomatoes generally. It's strong evidence for the health impact of these engineered compounds.
And it didn't stop there. They've made other super tomatoes.
Yeah, the same approach, using regulatory genes driven by specific promoters, has been used to create tomatoes high in other beneficial compounds, like high flavonols, another type of antioxidant linked to fighting age-related diseases.
And the resveratrol one, that number was
It
staggering.
really was. Resveratrol is the compound famous from red wine linked to heart health. They engineered a tomato where a single fruit contains the resveratrol equivalent of 50 bottles of red wine.
50!
Hmm.
That's efficiency.
It's certainly a concentrated dose. It shows the power of redirecting plant metabolism using these genetic switches.
And this GM technology isn't just for human food. The sources mentioned tackling a sustainability issue in fish farming. The fishy story.
Right. It's about omega-3 fatty acids, specifically EPA and DHA. We need them. They're crucial for brain health, heart health. We mostly get them from eating oily fish like salmon or mackerel.
But the fish don't actually make them, do they?
No, they get them from their diet, ultimately tracing back to marine microalgae or phytoplankton. The problem is, when we farm fish like salmon, we have to feed them fish meal and fish oil made from wild-caught smaller fish, like anchovies or sardines.
Which puts huge pressure on those wild fish stocks. It's not sustainable.
Exactly. So the goal was to create a land-based source of EPA and DHA. Scientists took an oilseed crop called false flax, Camelina sativa, and genetically engineered it.
No.
They introduced a set of 7 synthetic genes originally derived from marine algae. These genes provide the machinery for the false flax plant to take the shorter chain omega-3s it naturally makes and convert them into the valuable long-chain EPA and DHA right there in the seeds.
So you harvest the seeds, extract the oil, and you have a sustainable plant-based source of fish oil, essentially.
That's the aim. To create feed for farmed fish that doesn't rely on depleting wild marine resources. It's a major potential breakthrough for aquaculture sustainability.
All these examples, from the traditionally bred petunia to the GM tomatoes and flax, they inevitably raise the question of ownership. Who owns the genes? This brings us to intellectual property rights, IPR.
Yes, and it's a complex and often contentious area. Modern plant breeding, whether it's the years of effort for the black velvet petunia or the high-tech GM approach, requires enormous investment. Companies argue they need IPR to recoup those costs and fund future research.
We're a long way from just saving the best seeds year after year, like with the evolution of maize from teosinte. Now we have things like marker-assisted selection.
Right, MAS, using genetic markers to speed up selection, or direct genetic engineering. It's faster, more targeted, but also more expensive.
So what are the main ways companies protect these investments? The sources mentioned 2 key mechanisms: plant breeders' rights, PBR, and patents. What's the difference?
Okay, PBR is protection for a specific, novel plant variety. Think of the Cerfini petunias owned by Suntory. PBR gives the breeder exclusive rights to sell that specific variety for typically 20 to 30 years.
But it doesn't stop others from using that variety to breed new, different varieties.
Often, no. PBR usually includes exemptions for research and further breeding. It protects the finished product, the specific cultivar.
Patents, though, are different, stronger.
Much stronger, and this is where the controversy really lies. A patent can cover not just the plant variety, but the genetic trait itself, the specific gene or the method used to introduce it. Sometimes patents have even been granted on naturally occurring genes that were simply identified and bred into a commercial variety.
And that's the sticking point, isn't it? Patenting something that occurs naturally, even if it took effort to get it into a crop.
Exactly. Many groups argue that naturally occurring genetic traits should be part of the common heritage, available for everyone to use in breeding, and shouldn't be locked up by private patents, which also typically last 20 years. It's a constant tension between rewarding innovation and ensuring broad access to genetic resources, especially for food security.
It's fascinating how our ability to read, understand, and now rewrite genetic code creates these huge societal questions. We've talked about regulating plant systems. Now let's shift to another incredibly complex system, the human body and mind, specifically under stress.
Yeah, the human stress response is a masterpiece of evolutionary engineering. And the starting point in the sources is this really interesting observation. Your body reacts almost identically whether you're terrified or thrilled.
The racing heart, the sweating, the fast breathing. It happens if you hear footsteps behind you in a dark alley, but also if you, say, win the lottery.
Exactly. The physiological signature is the same. Psychologists differentiate between distress, negative stress, and eustress, positive stress like excitement or challenge. But the body's initial response is just Mobilization. Prepare for action.
Fight or flight, essentially. Get ready to do something demanding, whether it's running away or jumping for joy.
Precisely. And this mobilization is coordinated by the brain, specifically the hypothalamus, which kicks off two parallel processes almost instantly. The dual pathway,
Okay, pathway one.
the hormonal pathway. This is slightly slower but provides sustained energy. The hypothalamus releases a hormone called CRH. This signals the pituitary gland to release another hormone, ACTH,
ACTH travels through the blood.
to the adrenal glands, specifically the outer part, the adrenal cortex. This triggers the release of corticosteroids, the main one being cortisol. Cortisol's primary job in this context is to tell the liver and muscles to release stored glucose into the bloodstream, fuel for action.
Okay, so hormonal means fuel supply. What's the second pathway?
The nervous pathway. This is much faster, almost instantaneous. The hypothalamus sends a direct nerve signal down to the inner part of the adrenal glands, the adrenal medulla,
And that triggers.
the release of adrenaline, also called epinephrine. Adrenaline immediately activates the sympathetic nervous system. This is what causes the rapid heartbeat, increased breathing rate, dilated pupils, sweating, and it diverts blood away from things like digestion towards the muscles. It's the immediate go signal.
So why two pathways? Why the fast nerve signal and the slower hormone signal? Seems redundant.
The thinking is it provides both immediate readiness and sustained capability. Adrenaline gives you that instant jolt, primes you for immediate physical exertion. Cortisol ensures you have the energy reserves, the glucose fuel, to keep going if the situation, the stressor, persists for more than a few seconds or minutes. Speed and endurance built in.
Makes sense. The problem, though, isn't this acute response. It's when stress becomes chronic or when it interferes with performance. This is where that old psychology principle comes in, the Yerkes-Dodson law.
Yeah, established way back in 1908. It's fundamental to understanding performance. It basically says that performance improves as your level of arousal or stress increases, but only up to a certain point.
An optimal point.
Right. Beyond that optimal point, if stress or arousal keeps climbing, performance starts to decline, often quite sharply. We need some stress to be alert and focused, but too much overwhelms us. And that optimal point varies a lot from person to person and probably task to task.
This links directly to that University of Chicago study the sources detailed, looking at math anxiety. They specifically looked at working memory, WM capacity.
Right. Working memory is crucial. It's like your brain's temporary mental workspace where you hold and manipulate information needed for ongoing tasks, like holding numbers in your head while doing multi-step calculations.
And the study found something really counterintuitive about people with high working memory capacity. You'd think they'd always do better at math.
You would. But if those high WM individuals also had high math anxiety, their performance often plummeted. They actually performed worse, sometimes much worse, than people with lower WM capacity.
Why? What was happening?
The anxiety itself seemed to consume their working memory resources. The worry, the fear of failure, the intrusive negative thoughts, they cluttered up that high-capacity workspace they normally rely on for complex math strategies. There just wasn't enough mental bandwidth left for the actual math problems.
The stress became a cognitive distraction that hobbled their greatest asset.
Exactly. But here's the flip side. If a high WM individual had low anxiety, then the physiological stress response, measured by salivary cortisol levels, actually correlated with better performance.
So a little bit of that cortisol mobilization helped them focus, as long as they weren't anxious about it.
It seems so, the eustress effect. The hormonal surge was beneficial when it wasn't accompanied by paralyzing worry.
And what about people with low working memory capacity?
Their performance was less affected by anxiety levels, interestingly. The hypothesis is that they might rely on different, perhaps less WM-intensive strategies, maybe more rote memorization, or simpler procedures. So even if anxiety used up some WM, it didn't disrupt their primary approach as much.
Okay, so pulling this together, what's the big takeaway for you, the learner, trying to manage stress or performance pressure?
The crucial insight is the power of the cognitive loop. The whole stress cascade really kicks into high gear only when your cortex, your thinking brain, interprets a situation as a threat or a major stressor.
It's the perception that matters.
It's hugely important. Because the cortex communicates with the hypothalamus, you can consciously influence that initial trigger. This is the whole basis for things like cognitive behavioral therapy, CBT.
Changing your thoughts to change your feelings and physiological responses.
Exactly. By identifying and challenging negative self-talk, by building confidence in your ability to handle the task, what psychologists call self-efficacy, And by reframing the physical sensations of stress as activation or readiness rather than panic, you can dampen the anxiety response. Especially for those high WM individuals, this can prevent the cognitive interference and allow them to perform at their peak.
It's fascinating. Regulating internal states, whether it's pigment production in a plant or hormonal balance in a human, seems to hinge on these control mechanisms. Now, let's take this idea of control and measurement to a whole different scale analytical science, from crime labs to outer space.
Okay, shifting gears dramatically now to analytical science. At its core, this field is about answering two fundamental questions about any substance or sample.
Which are?
Qualitative analysis, what is in this sample, and quantitative analysis, how much of it is there?
Seems simple, but the applications are everywhere, aren't they? Forensics, environmental testing, medical diagnostics, quality control.
Absolutely everywhere. Think about testing quartz. Drinking water regulations might require checking for 30 or more different pollutants down to tiny concentrations, or analyzing evidence from a crime scene, or confirming the purity of a pharmaceutical drug.
And in all those cases, the results have to be absolutely reliable. You can't have ambiguity.
Reliability is paramount. Analytical methods have to be rigorously validated. Scientists need to prove their methods are accurate, close to the true value and precise, giving the same result repeatedly. Often they aim for better than 95% accuracy and precision, especially when health or legal decisions depend on the results.
The sources used sports anti-doping as a really good example of quantitative analysis in action, specifically catching athletes who use blood doping.
Right. Blood doping aims to increase the oxygen-carrying capacity of the blood by boosting hemoglobin levels, usually by transfusing stored blood. If it's donor blood, you might detect foreign antigens. But if it's the athlete's own stored blood, autologous transfusion, it's much harder to detect.
So how do they catch it?
One key way is by looking for indirect chemical markers. Blood is typically stored in plastic bags, and these bags contain plasticizers, chemicals that make the plastic flexible. A common one is DEHP.
DEHP, diethylhexylphthalate, okay.
Now, tiny amounts of DEHP can leach from the bag into the stored blood. So when the blood is reinfused, the athlete gets a dose of DEHP metabolites along with it.
But wait, isn't DEHP kind of everywhere in the environment? Plastics, food packaging?
It is, which is the challenge. Every person has a low background level of DEHP metabolites in their system.
Okay.
So analytical scientists can't just look for the presence of DEHP. They have to do precise quantitative analysis to see if there's a sudden, significant spike in the concentration that rises statistically above the athlete's normal baseline level.
Ah, it's the change from their normal level that indicates doping, not just the presence. That requires incredible sensitivity. What tools do they use?
The workhorse instrument for this kind of trace-level drug and metabolite detection is liquid chromatography mass spectrometry, usually abbreviated as LCMS.
LCMS, how does that work, basically?
Think of it in two stages. First, the liquid chromatography, LC part, separates the complex mixture like urine or blood plasma into its individual chemical components. It's like a very sophisticated filter that lets different molecules pass through at different speeds based on their chemical properties.
Okay, so it sorts the chemicals out, then the MS part.
Then the separated components flow into the mass spectrometer, MS. Here, the molecules are turned into ions, given an electrical charge, and then accelerated through a magnetic or electric field. This field deflects the ions based on their mass-to-charge ratio.
So heavier ions get deflected less, lighter ones more?
Essentially, yes. The detector measures how many ions of each specific mass-to-charge ratio arrive. This creates a unique mass spectrum for each compound, a fingerprint based on its molecular weight and fragmentation pattern. So MS tells you what each separated component is, and by the intensity of the signal, how much of it is there.
It's incredibly powerful. But the sources mentioned a constant cat-and-mouse game with designer drugs?
Always. Illicit chemists are constantly tweaking the structure of banned substances, maybe changing just one small part of the molecule to create something new that might enhance performance, but won't be picked up by existing LCMS detection methods because its fingerprint is different.
So the analytical scientists have to constantly update their methods, anticipate these changes, and add new fingerprints to their libraries.
It's a never-ending race to stay ahead. Now, let's take this principle of using precise measurement to detect something hidden and apply it on the grandest possible scale, finding planets around other stars.
Right, finding Proxima b, the planet orbiting Proxima Centauri, our nearest stellar neighbor, just 4.2 light years away. Discovered in 2016, we can't actually see the planet, can we?
No, it's far too small and dim compared to its star, even though Proxima Centauri itself is a faint red dwarf. The planet is about 1.3 times the mass of Earth, orbiting very close to its star, completing a year in just 11.2 Earth days.
So if we can't see it, how did we find it? How did we measure it?
Using a technique based on the Doppler effect, similar to how the pitch of an ambulance siren changes as it moves towards or away from you. It's called the radial velocity method, or sometimes the Doppler wobble method.
Wobble. The planet makes the star wobble.
Exactly. Even though the star is vastly more massive, the planet's gravity still exerts a tiny tug on it. Both the star and the planet actually orbit around their shared center of mass. Because the star is so much heavier, this center of mass is very close to the star's center, but not quite identical. So the star makes a small orbit, a tiny waddle, in response to the planet's pull.
And we can detect that tiny wobble from 4.2 light years away. How?
By looking very, very precisely at the star's light spectrum. As the star wobbles towards us in its tiny orbit, the light waves it emits get slightly compressed, shifting the spectral lines towards shorter wavelengths, towards the blue end of the spectrum. This is a blue shift.
Okay, moving toward us, blue shift.
And when the star is wobbling away from us, the light waves get stretched out, shifting the spectral lines towards longer wavelengths, the red end, a red shift.
So astronomers measure this tiny, cyclical shift back and forth between blue and red in the star's spectral lines.
Precisely. The period of this blue shiftward shift cycle tells us the planet's orbital period, 11.2 days for Proxima b, and the amplitude of the shift, how much the wavelengths change, tells us how fast the star is moving, which in turn allows us to calculate the minimum mass of the planet causing the wobble.
It's amazing, weighing an invisible planet by the wobble it induces in its star, trillions of kilometers away. It's quantitative analysis on an astronomical scale.
It really is a triumph of measurement science. But finding the planet is just the first step. The big question is, could Proxima b actually be habitable? Sources outline some major challenges.
Yeah, it orbits very close to its red dwarf star, so it's probably tidally locked, right? One side always facing the star, one side always facing away.
That's highly likely, which would mean one side is potentially scorching hot and the other side is permanently frozen in darkness.
And red dwarfs emit much less visible light than our sun.
Right. Proxima b probably receives only about 2% of the visible light Earth gets. It would be perpetual twilight on the day side. And without an atmosphere to trap heat, its estimated average surface temperature would be a frigid -40 degrees Celsius.
Minus 40 C, okay. Not sounding very habitable yet. What could change that?
An atmosphere. That's the absolute key. If Proxima b has a substantial atmosphere, modeling suggests it needs at least 30% of Earth's atmospheric pressure, then winds could potentially circulate heat from the hot day side to the cold night side, moderating the temperatures.
And an atmosphere would also offer protection. Red dwarfs can be quite active, sending out flares of radiation.
Crucial protection, yes. Shielding from UV and X-ray flares would be vital for any potential surface life. So the next big observational goal is to try and detect an atmosphere around Proxima b and analyze its composition.
Looking for signs of water vapor, maybe oxygen, methane biosignatures.
Exactly. That's a task for incredibly powerful telescopes, like the James Webb Space Telescope or the next generation of giant ground-based telescopes currently being planned, like the ELT or GMT, with mirrors 20, 30, even 40 meters across.
But observing is one thing. The sources ended with something even more ambitious. Actually going there. Breakthrough starshot.
Yeah, this is stepping into science fiction territory, but with serious engineering behind it. The problem is distance. Even at 4.2 light years, Proxima Centauri is incredibly far, about 40 trillion kilometers. Our fastest current spacecraft would take tens of thousands of years to get there.
So Breakthrough Starshot proposes a completely different approach. Tiny spacecraft.
Microscopic, almost. The concept involves launching perhaps thousands of tiny probes called star chips. Each would weigh only a few grams, basically a chip carrying cameras, sensors, and communication gear attached to a solar sail about 4 meters wide.
A sail pushed by light.
Pushed by incredibly intense light. The plan is to use a massive array of ground-based lasers, all focusing their beams onto one sail at a time. They deliver a colossal amount of energy, about 1 terajoule, which is huge, over maybe 10 minutes.
And that laser push would accelerate the star chip to
We're about 20% of the speed of light, an absolutely staggering velocity.
10% of light speed. And at that speed, the journey to Proxima b would take.
Only about 20 years. Still a long time, but within a human generation, making interstellar exploration seem potentially feasible for the first time. It transforms the search for Earth 2.0 from passive observation into an active, albeit long-term, mission goal. Hashtag outro.
Wow. Okay, that was definitely a deep dive, maybe our most wide-ranging yet. We went from the deep velvety darkness of a petunia.
Driven by high concentrations of anthocyanins, understanding that the regulatory genes controlling those pigments evolve nearly twice as fast as the structural genes doing the work.
Then we saw how that genetic knowledge is being used to engineer purple tomatoes packed with antioxidants that extended lifespan in mice, and even creating sustainable omega-3s in plants.
We pivoted to the human stress response, the Yerkes-Dodson curve, and how managing cognitive anxiety, especially for high performers, is key because perception drives the hormonal cascade.
And finally, we scaled up to analytical science, from detecting doping using LC-MS to finding Proxima b via the Doppler wobble of its star, and even dreaming of reaching it with laser-propelled nanograph.
The thread connecting it all really is the power of precise observation, measurement, and understanding control mechanisms, whether it's a gene network, a hormonal system, or the gravitational dance of stars and planets. Knowledge through analysis.
So as we wrap up, here's a final thought for you, the learner, something to chew on, linking back to those fast-evolving plant genes.
We discovered that the regulatory genes, the transcription factors, evolve quickly because they tend to have very low expression levels. It seems biological systems achieve major shifts by tweaking these subtle, low-volume control signals.
So the provocative question is, if nature's big evolutionary leaps often come from subtle changes in these low-expression regulators, what unrecognized low-level regulatory shifts might be quietly driving the next significant evolution in, say, human potential, performance, or even consciousness? What subtle dials are being turned that we haven't measured yet? What stands out to you?
Lots to think about there.
Indeed. We'll leave you with that. Thanks for joining us on The Deep Dive.